available may refer this video later. So we share the slide. Okay, hold on. Can you guys see the slide? Okay.
No rồi.
So today we will enter a new chapter of the renewable energy, which is the tidal and wave energy. So particularly, this is one of the renewable energy resources, but not that
Slide tak
very
ada.
popular
Slide
to
tak
our
ada.
country. But then at least we know the idea or the concept of it, so that it can give the enrichment of our knowledge related to the source of the renewable energy. Before we go further, let's say so we share
Hello, sir.
some sort of the video related to the renewable energy. Hold on,
Sir, slide tak ada.
Slide tak ada, sir.
where is hold on. Okay. Okay, so we share the video. Okay. So share the video. Can you guys see the video?
Yes, doctor.
Anyone?
Electricity. Tides are caused by the combined effects of gravitational forces exerted by the moon, the sun, and the rotation of the earth. Tidal plant.
Can you guys see the video? Is that okay for you guys?
Okay, doctor.
Be installed along.
All right, thank you very much. So start to.
Tidal power is a form of hydropower that converts the energy from the natural rise and fall of the tides into electricity. Tides are caused by the combined effects of gravitational forces exerted by the moon, the sun, and the rotation of the earth. Tidal plants can only be installed along coastlines. Coastlines often experience 2 high tides and 2 low tides on a daily basis. The difference in water levels must be at least 5 meters high to produce electricity. Tidal electricity can be created from several technologies, the main ones being tidal barrages, tidal fences, and tidal turbines. Tidal barrages are the most efficient tidal energy sources. A tidal barrage is a dam that utilizes the potential energy generated by the change in height between high and low tides. This energy turns a turbine or compresses air, which in turn creates electricity. Tidal fences are turbines that operate like giant turnstiles, whereas tidal turbines are similar to wind turbines, only underwater. In both cases, electricity is generated when the mechanical energy of tidal currents turns turbines connected to a generator. The generator produces electricity. Ocean currents generate relatively more energy than air currents because ocean water is 832 times more dense than air and therefore applies greater force on the turbines. Tidal power is easy to install and renewable, having no direct greenhouse gas emissions and a low environmental impact. Because the ocean's tidal patterns are well understood, tidal energy is a very predictable energy source, making it highly attractive for electrical grid management. This sets it apart from other renewables that can be more unpredictable. However, adoption of tidal technologies has been slow, and so far, the amount of power generated using tidal power plants is very small. This is due largely to the very specific site requirements necessary to produce tidal electricity. Additionally, tide cycles do not always match the daily consumption patterns of electricity and therefore do not provide sufficient capacity to satisfy demand. That's tidal power.
All right, so that's related to the tidal power. Okay. Okay. Okay, so we will start the class. So technically, get this slide from the Stephen Martinez, Nota Matthew Nota, and Brother Burnham. So we use their slide for the lecture today. Basically, this is the history of the tidal energy, which related after some time now. So in 1966, 2001, 2002. So there's a state or country that use this tidal energy, but unfortunately on our side, maybe that is not very resourceful for our side due to the certain consideration as per mentioned earlier in the video. But then it's also one of the option that we can translate or convert the energy from the resource of the renewable energy as a part of the wave or tidal to convert in the form of the energy. But if you notice, they're more or less the same like the previous that we have learned. For example, for the wind, we require the movement of the wind to rotate the blade. For the hydro, we need the movement of the flowing water to rotate the turbine. And this case as well, related to the wave, so it still can make a free and abundant move to our mechanical system to convert it in a form of the energy, and of course related to the generator and producing the electricity by having their own dedicated connection. Okay, so this is the glance through related to the wave energy. Okay, of 1790, first patent, a device designed to use ocean wave to generate power. 1910, first oscillating water column was built by Boss of Pratusquake to power his house. 1940s, Yoshio Masuda experiment with many concept of wave power. 2004, wave power was delivered to an electrical grid for the first time. Okay, so that's the movement lah, related to the wave energy work. And then there's also related to the tidal stream generator, very close in concept to traditional windmill. Okay, most popular prototype on the market. Prototype site include Norway, England, and New York. Okay, also in 2007, 8 prototype turbines were placed in the East River between Queens and Roosevelt Island. It's the first major tidal power project in USA. Power 1/3 of a parking garage and a supermarket. So there's a lot of work previously related to the wind or tidal energy that others country. And then the CGen, okay, CGen, world first large-scale commercial tidal stream generator. Okay, so this is how it should look like. Okay, so this is the blade, a 2 blade only at the center of the ocean. First one is installed in the Stormford Narrow Island. Okay, Stormford Island. Generate 1.2 megawatt between 18 to 20 hours a day. Okay, blade span 16 meter in a diameter. So this is the sample, how it look like related to the tidal energy. And of course, since it related to the mechanical system, so it also provide with the equation or formulation that we can expect to obtain or generate the power. Okay, so P representing the power in watts. Okay, so this is the efficiency, okay, efficiency of the turbine efficiency, which normally given based on the product basis. Okay. And then the rho is the density of the water. Since we are using the water is a substance to rotate our blade. And then A is the swept area of the turbine, that area that can be covered as the area of the round shape of the area based on the turbine blade. And the V is the velocity of the flow. This flow representing the flow of the movement of the tidal or the seawater. Okay. And then of course power by 3 lah. So power by 3. So it more or less similar with the wind energy, but in this case we are using the properties of the water instead of the air. And then, so this the barrage tidal power raise power system. Okay, so how it look like. So located, one of the cases is located on the France River of France, 750-meter long, with the 24 turbines. Just imagine 24, meaning that it can be parallelly installed at the corner of the river. Okay, 750-meter long. Okay, capacity 240 megawatt, annual output 600 gigawatt hour, supply 0.012% of the France power supply, which is open for the last 1966. Okay, so this is how it look like. Tides coming in, and then from the front, it will rotate the blade. Okay, and then after some time, when the tidal going through the other session or other season, and then with the several partial of the time, and then when the tide is going out, we still able to rotate the blade, meaning to say, uh, as long that our tidal, I mean the seawater experience the tidal either in or out, or there's any movement of it, then it manage to rotate the blade, which is the moment we rotate the blade, and then the power will generate and transfer to the generator, and then the generator will transmit to the distributor, to the grid, and distribute to the electrical appliances user. Okay, so that's the basic concept of it. And then for the case of the bearish tidal power just now that we see, so approximately more or less the same, it's just the method of the notation of the equation. So E representing the energy, half A is the horizontal area of the bearish basin. Okay, rho is the rho of the density of the water, okay, sea water. And then G is the gravity, and then the H, this capital H, but actually this is a small h, vertical tide range. Okay, so it's power of 2. Okay, and then the potential energy available from the barrage is dependent on the volume of water. Okay, so that's the thing. Okay, so basically, so the environmental impact of it. Okay, so the environmental of it, mortality rate of fish swimming through the turbine is around 15%. So it's a quite sad because he sacrificed 15% of the fish. I mean, our consumption of the fish, 15%. Sonic guidance to get fish to avoid the turbine. Okay, so this one is the things that try to avoid to minimize the 15% by having the sonic guidance to to disperse the fish nearby the barrage, okay, or the tidal area. And then placement of the barrage turbine into the estuaries can change entire ecosystem because the outer flow of salt water possibly change hydrology and salinity, and the sediment movement also can affect the ecosystem of that particular area. Okay. As per mentioned earlier, it more or less similar with the wind energy, but in this case, we are using the water or seawater as a medium of the movement. But when we can see over here, a tidal stream generator draw energy in the same basic way wind energy do. Okay, so in this case, higher density of the water allow a single generator to provide significantly more power. Since we know the density of the water much more greater compared to the density of the air, so maybe that's one of the advantage of having the tidal or the wave energy. And yet, water speed of nearly 1/10 speed of the wind can provide the same energy output. But the drawback of it may be the flow, the velocity of the wind not that high as the wind energy. So, but then we can try to compensate that based on our calculation just now to see what is the best condition to represent the effective power by the wave energy or to the wind energy. And yet, later, current in water is much more reliable than the wind in the air. So, meaning to say, since there's a movement of the tidal on the water, either in or out movement, in-out movement, or the movement as long in any direction of the water, it's still able to move the turbine blade, and of course will generate the electricity through the generator and then transmit to the grid and distributor. Okay, so that's the idea. Okay, so before we go to the economic of the tidal power, so want to share another video that you can see afterward. Okay, hold on. Hold on. Okay. Okay, so
Thing that could have changed the story of energy. Professor invented something that could have changed the story of energy. This contraption, called the Edinburgh duck. Don't blame me, I didn't name it. But if you squint really hard, you can sort of see it. Anyway, the duck's butt bobs up and down with waves to generate clean electricity. It attracted a lot of attention from the UK government and press around the world because it had huge potential. Waves are everywhere, consistent and full of power. But nothing came of it, just like the countless other sci-fi looking wave energy devices invented in the following decades. 40 years later, we still only get a laughably small amount of energy from waves globally. But that might soon change.
We're going to start seeing this technology out in the ocean in the next, couple years, really.
So what's happened to the duck and all these technologies? And will wave power ever live up to its potential? For at least 200 years, people have tried to figure out how to harness the ocean's energy. Over 1,000 patents have been filed, and they all pretty much look different. Because unlike the wind industry, which is more or less converged on an optimal design, the horizontal axis turbine, wave power is still in development. Because waves are complex, they don't just travel in one direction like the wind, so you can't just stick a turbine in somewhere. Let's zoom out a bit to understand. Waves form when wind blows over the ocean. Friction between the moving air and the surface of the water causes ripples that eventually grow to form waves. The size of waves depends largely on three things: the strength of the wind and how long and far it blows unobstructed over a stretch of water. Which is why you find the biggest waves and the best surfing spots along the western coasts of North and South America, Europe, and parts of Africa and Australia. So with waves, it's not that each particle in the water travels from ocean to coast. Instead, each one remains almost in the same place, moving in a circle as it gets energized by the wind. The energy is then transferred along to the next particle and so on. They move with the most intensity at the surface, dwindling the deeper you go. Which kind of explains the sheer diversity of devices that attempt to capture different kinds of movement. At the surface, near the seafloor, and at the coast. So waves are complex, but we can still predict how they're going to flow. Satellite data on wind can help understand wave swells days in advance. There are various basic designs, but here are a few main ones. A point absorber. It floats at the surface and absorbs energy from all directions, while staying connected to the seafloor. The relative movement between the buoy and the stationary part moves a piston inside into an energy conversion system that drives a generator. A surface attenuator, which is made up of multiple floating segments connected together and placed perpendicular to incoming waves. The relative motion between each segment once again powers an energy conversion system. And third, the oscillating water column, a partially submerged hollow structure. As waves enter it, they compress and decompress the air column and push it through a turbine, which connects to a generator. The duck belongs to a category called the terminator, similar to the surface attenuator. There are also devices that are attached to the seafloor, whose up and down or sideways flapping movement generate electricity through the relative motion. Still others that are installed closer to the coast, where waves crash. Some of these concepts have existed for centuries. They all work. But it's their performance in real-world conditions over the long term where the big question mark lies.
It's an extremely hostile and complex environment to place anything in the ocean, and to generate consistently, reliably, and over a very long period of time to generate power from that environment is really challenging.
Matthew Hannon researches technology innovation and has dived deep into the history of wave power. By hostile, he means that salt water is so corrosive, it eats up most metals over time. And marine creatures begin to use it as a base to live on, slowly breaking it down. Corrosion-resistant alloys like steel are available, but they're inherently costly. Underwater devices also need maintenance, which means divers, boats, and platforms. So even at the testing stage, the investment that wave power needs is incredibly high. But cost is not the only problem. Another major one is competition. The Edinburgh Duck was supposed to be a solution to the energy shortage following the oil crisis in 1973. But by the time it was ready for testing, the nuclear industry was receiving so much more attention that the duck lost the race.
From the late 1980s into the late 1990s, it was very quiet, very little funding available, and then its renaissance from the advent of the millennium basically onwards.
This time, two companies tested wave energy devices off the coasts of Portugal and the UK. The first was an attenuator, inspired by the duck, but with a much more complex design and set up completely offshore. The other was a submerged flap, also offshore. Both had more reliability issues and required more maintenance than their manufacturers expected. And so after months of testing, investors lost interest. They had to shut up shop. And like in the first instance with nuclear, this time wave power was pushed to the fringes by onshore renewables like wind and solar, whose prices had fallen by up to 3 and 10 times respectively in the 2010s. But similar to the 1970s, we're facing another energy crisis today, the need to get to net zero emissions, even as the demand for energy is rising. Estimates predict an average 30% rise in demand by 2045. And here's where wave power comes back into the game. On a dark, gloomy winter's day where the sun isn't shining and the wind isn't blowing, alternatives, including tidal and especially wave power, have a big role to play. Not only are waves predictable, they're reliable. Waves flow almost consistently all year round. Wave energy devices can also generate several times more power for the space they occupy compared to wind turbines, simply because they're smaller and water is hundreds of times more dense than air. Environmentally speaking, some machines could disturb the seafloor habitat and create noise, and this needs to be considered. But early indications are that the impact is relatively low. And since most devices float along with the current anyway, they're unlikely to hit marine mammals.
So the story continues at this point.
Several devices are now back in the water. In Australia, a few companies are seeing success. One array of submerged buoys even connected a device to a local grid. The US Navy recently invested $6 million into testing devices off the Hawaiian coast. And a Japanese professor and his team are trying out a new operating principle, this time putting small turbines close to the coast. In 2021, Europe installed 3 times more capacity in wave power than the previous year. Both public and private investments rose significantly, totaling 70 million euros in both tidal and wave power. While in theory, the potential for waves is 3 times today's global demand, it's estimated that by 2050, wave power will generate 10% of global power, which is a significant share. The biggest testing facility at the moment that's arguably showing the most potential is in Scotland, the perfect location with its strong winds, large swells, and history of testing wave devices. The Scottish government has even created a system of supporting companies to learn from the mistakes of others. One company testing at the moment is Motion Energy. They simplified their devices and looked to attach them to existing infrastructure for easier maintenance. They also looked for niche markets.
And kind of ironically, where we ended up was in oil and gas.
It sounds like an oxymoron, but you heard that right. Oil and gas companies have the money, the infrastructure, and the need for energy where waves can produce it.
It was a good economic opportunity. So we always saw this sort of oil and gas as a good high value market, but it's also a stepping stone to other markets.
Industry analysts say wave power is behind wind by around 20 years, and it won't catch up with or replace either wind or solar anytime soon. But right now, it's alternative markets like offshore oil rigs and less problematic ones that do look promising. Like islands. There are around 2,000 islands with less than 100,000 inhabitants that lack grid connection and use diesel generators for energy. As we head towards a zero carbon world, wave power could be the perfect resource here, and several companies are looking at various islands already. Others want to attach devices to platforms in the aquaculture industry.
In longer term, where we see wave energy fitting in terms of the total impact it can have, is being combined with offshore wind.
Sin Power in Germany is one company working to attach wave power devices to offshore wind platforms that also have solar panels and the infrastructure for grid connection. Eco Wave Power in Israel has attached them to breakwaters and piers that feel the effect of the most aggressive ocean waves. At the moment, neither the capacity of installed wave power nor the cost of the energy it can produce compares to other renewables. But its value lies in the diversity it can bring to the mix. To make wave power viable, the industry needs to follow a path similar to other renewables with support and investment, plus time to test. As more devices test and produce power, economies of scale will bring the costs down, like they did for wind power. And waves can fill a gap that other renewables cannot. Do you think wave power's time has finally come? Let us know in the comments below. And don't forget to come back every Friday.
Hmm. Okay, so we back to the notes. Okay. Okay, so basically, so that's the concept or the big idea of the wave energy or tidal energy that currently has been developed by the industry, by the researcher. And yet, as per mentioned, it's a quite crucial when we go for the tidal or wave energy due to the initial cost, because of course, as you can see just now, it's related to the investment, checking, maintenance, and everything under the sea to ensure everything goes well and work efficiently and if and work well. I would say that kind of the situation. Okay, so the economic of the tidal power, the cost of building a tidal power plant can have a high capital cost in the range of the 15 billion for 8,000 megawatt. At the Philippines, 3 billion to 2,200 megawatt. So operating costs are low and usually come from maintenance. Okay, so as per mentioned, this related to the initial cost to install the things. But then we need also the maintenance throughout the system to ensure it can work well as part as the concern. So then, what you can do in the Amazon helical turbine technology being used to generate small-scale electricity for rural community, and then that rural resident, okay, are dispersed and cannot be reached economically by power lines from central generator. The only decentralized option available to them now are solar panel and diesel generation. And then the configuration, the helical turbine rotates on a shaft with a pulley that runs an alternator by means of a belt, and the alternator changes battery. So this is the consideration of the some figures. So this was a very conventional approach to produce the project related to the wave or the tidal. Okay, in this case, they have this kind of the rotating pulley and belt to exploit the movement of the tidal and the seawater to generate the power by having this kind of blade. Okay, and then they managed to install with the 8 solar panel, 75 week peak, watt peak. Can install 5,000 plus, and then the energy generation in the front of the 2,800. And then by combining these both, they managed to have this kind of option. So if you can see from the project and also from the video, it start to go for the hybrid version, which is the tidal, maybe not that alone. They might consider it's a part of the hybrid with the solar and of course related to the wind energy as well. So, but then it depends on the how good the research towards it, because by having that kind of option, yes, technically we managed to obtain many source of the RE at a one time with a single device from the movement of the tidal wave, and then from the wind as well, okay, and then the solar as well. But then of course it related to the cost or the technology that we need to cater nicely so that it can work well and accordingly to obtain the desired output based on the investment that we've been put on the system. Okay, and then the wave power that you see from the video, there's a salter duct design, which is the shape like the duct. Okay, and then it just to try to exploit the movement of the wave, and then by having the movement of the waves, it can be a movement to the duct, the duct shape, and then from the movement from the mechanical parts of the duct, then it can translate to the generator, and of course go to the transmitter, and go for the power distribution. But then we need or required maybe numbers of duct lah kan, numbers of duct, which is not only one, it can be maybe 50, 100, 150 to 100, so that they can generate more power throughout the movement of the duct. Could stop 90% of wave motion and convert 90% of that to electricity. Shut down because an error in calculating the cost, which wasn't discovered until 2008, and the program has been shut down in 1982. Okay, right? Okay, so this is the thing, how it's work. Okay, how it's work. The duct device both are back at force as wave pass. Okay, so this is the movement. Okay, the movement, and then this is the generator. The moment move the pendulum that is connected to a generator that produce electricity. Okay, so then you just imagine we want to have this one, but then we need to tie it to the ground. So another cost, another maintenance we need to add on. But then actually what we are trying to do, we try to harvest this movement and convert to the generator and transmit all the things accumulatively to the generator and the grid. The wave device opposite incorporate an electricity generating system based on the pendulum connected to a generator. Okay, as the salter duct moves up and down to the wave on the wave, the pendulum swing forward and backward, generating electricity. Okay, so to get the more power, then we have the more ducts. Okay, and maybe that's the thing related to the cost when we need to hold this kind of uh, ties on the ground to ensure it's not running away from the location. Okay, so that's the thing. And then some company design mechanism, vegan, limper, ocean power delivery, plumbing tube, renewable energy holding, CITO or stir wave energy device. So this is the only technology from the others company to propose to get to harvest the energy from the wave or the tidal system. Okay, and then so try to go another video to share with you. Hold on. Okay. Hmm.
Thanks us all. Our search for alternatives for the global climate change affects us all. Our search for alternatives for emission-free energy generation has led us to the enormous potential of the oceans. The seas of the world hold tremendous energy that can be utilized, for example, in the tidal streams. Void Hydro develops a turbine for the utilization of these tidal currents, with which this enormous energy can be converted into electric power. According to expert opinion, approximately 400 terawatt hours per year can be won in this way from the seas of the world. The dimensions of a tidal current turbine are impressive. The turbine nacelle is almost 13 meters long, and the rotor has a diameter of 16 meters. In total, the plant is 26 meters high, which amounts to the size of a 7-story house. Once the installation vessel has reached the intended location for the underwater power station, the turbine is connected to a pre-placed subsea cable. For the future recovery of the turbine for maintenance purposes, guide chains are fixed to the foundation. The entire unit can now be immersed. After the underwater power station has reached the ocean floor, the turbine is started from the onshore control room. The sea current sets the rotor into motion, and the turbine begins to supply electricity with a generation pattern following the tides, regularly, predictably, and reliably. Each turbine has an installed power of 1 megawatt. The tides change their direction of flow approximately every 6 hours. The special rotor design of the turbine allows flow intake from both ends without having to adjust the turbine. The rotor simply changes its direction of rotation. This means that no complicated equipment is required for blade adjustment or nacelle rotation. During the development of the turbine, special attention was paid to simplicity, robustness, and eco-friendliness. The design has eliminated failure-prone transmissions and operates without oils and grease. Seawater is used for bearing lubrication. Another special feature lies in the avoidance of complex and sensitive seals. This has been achieved by designing the generator components to operate immersed in seawater. Via the sea cable, the generated electricity is directly transmitted to an onshore inverter station, then fed to the grid via a transformer. This robust and simple subsea technology gives long intervals between maintenance and hence minimizes the utilization of extremely expensive marine equipment. When the tidal current turbine is due for maintenance, the facility is shut down and disconnected from the grid on shore. For maintenance, the turbine is lifted from the water. To achieve this, a service vessel positions a cradle over the turbine. Buoys connected with the guide chains during installation float to the water's surface in response to an acoustic signal, and this allows access to the guide chains. Sliding on these chains, a lifting frame is lowered and directed below the turbine by maneuvering the vessel. The hydraulic clamp closes and then grips the turbine nacelle. Now the guide chains are tightened and the turbine can be safely lifted to the surface and disconnected from the sea cable. All maintenance work can be performed directly on the service vessel, protected by the harbor walls. The rotor blades are removed. The turbine is lifted to the service vessel and put on mobile assembly carts. Secure on these assembly carts, the nacelle can be easily disassembled, allowing good access to all components that require maintenance. Even in small harbors with little infrastructure, the components can be exchanged easily and quickly with comparatively simple equipment, for example, a mobile crane. After completion of the repair or maintenance work, the turbine is returned to its location at sea and reinstalled. With its new tidal current turbines, Voigt Hydro is making a vital contribution to the development of new and emission-free energy generation. The company regards itself as a pioneer in technology developments aimed at the utilization of all kinds of hydropower. Voigt, engineered reliability.
Okay, so that's the thing. Um, okay, so then when we see the things, it seems like quite challenging in terms of the maintenance. We need to take all the things from the sea and then going back to the onshore and then do the maintenance or replacement and then later install it back to the sea. Okay, so that's how it look like basically. So based on that kind of scenario, so it also offer the advantage and disadvantages for the tidal or the ocean system, or sorry, for the wave system to produce the energy. So advantage, the energy is free, okay, no fuel needed, no waste produced, not expensive to operate and maintain, can produce a great deal of energy. So this the claim of the advantages of the wave or tidal energy. But then it also have the disadvantages. Okay, so it depends on the wave. Sometimes you will get lots of energy, and sometimes almost nothing. Okay, so meaning relatively low. Okay, needs a suitable site. That's the things mentioned repetitively. So we need to assess the condition or the behavior of our wave or tidal, so that we can know is that what is the potential or expected energy that we can produce, while we have to give the effort, the energy, the time, and then also the investment related to the cost for that particular item or system, and of course the technology as well. Wave are consistently strong, okay? And then some design are noisy, okay? Some design are noisy, but then again, so wave, so any noise is unlikely to be a problem. Meaning to say, if we manage to produce the system related to the noise pipe, but actually it can be compensated with the noise of the wave itself. So it seems like there's no issue related to the wave, sorry, noise due to the naturally the wave is have the sound, right? So it can be compensated of that. But I think the idea is that if we manage to produce as not high noise, meaning to say more or less similar with the wave sound, they should be fine. But if you're greater than that, it can be another part of the disadvantage of the system. Okay, so and then must to be able to withstand. So withstand mean to withstand with the the condition of the wave, which is very unpredictable, and also the undersea of the condition. And then for the environmental impact that we can see, noise pollution. Okay, noise pollution displace productive fishing site. Okay, so by having that kind of thing, maybe it jeopardize the strategically area that fishing site perhaps. So that we need to consider as well. Change to the pattern of the fish and the sand nourishment. So yes, by having that kind of thing, it may be alter the maybe the ecosystem in the under the sea. So that's the thing that we can't see it clearly. But alter food chain, of course, by having the changing of the ecosystem, and it can disrupt the migration of the pattern. And offshore device will displace bottom dwelling organism where they connect into the sea, okay, into the sea. So that's the thing we try to share today. So stop sharing. Hold on. Stop sharing. Okay, stop sharing. So kita get back to the class, and then so also stop recorded version, so that not that long in terms of the recorded version later. Stop recording. Okay.